This is Science Max, Experiments at Large. Science Max! Gravity, gravity, gravity. Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max, Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Looks straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it, make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. We're gonna, oh yeah, I gotta clean that up. We are going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
Oh, hi, Phil. Good. What? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To replace the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa! Gravity defy. Gravity defy. Gravity Look at it fly! Defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why.
When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it.
Until there's no more tension, and then the top passes the bottom and the whole thing. That is how it works. But here is the real question.
Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring!
Let's max it out! Bring it. Don't tangle it. So now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go!
A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it.
So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa.
Sonia and I are maxing out the hoop glider out of bigger and better materials.
This is the largest tube I have, right?
A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and...
Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
It's pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited.
we take our plastic and metal hoop glider outside to test it and...
Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it?
Sonia and I made a very solid design, but the problem with it became pretty obvious.
Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down. So you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon and it was, it had a, There. A giant balloon. And look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Oh. Towards the center of the Earth. Eh? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes, gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy.
Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground. I see.
so we need something that's light
Light
and something that's strong.
and strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out.
Hoop glider dance! Okay, 3, 2, 1.
That's pretty good.
That was
Pretty
amazing.
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good.
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it.
Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I
made this!
made a slightly heavier one.
Let's do it.
Okay, 3, 2, 1, go! Not bad. My turn.
Here we go.
Okay. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before. to
And
see-
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome.
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But I
we can
think
make
that sounds great, though.
I think make a big slingshot for this?
Why not?
Okay, high five. Let's do it. This is an egg. Eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way, because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over, good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide. Look closely, it's the same location. Amazing. But did you know that this is caused by the gravity of the moon and the sun? See, this cookie is the Earth. And this little happy fellow is me. Hello. And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well,
That was
Pretty
amazing.
good. Here we go.
but we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more could you ask for?
Well, my turn.
Hey, see you next time.
Science Max!
Try yours.
What makes airplanes, or basketballs, or people fly? It's air. As well as a bunch of other things that we learn when we try to make a giant paper airplane.
So that didn't work.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ho-ho! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast, because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom, where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that, and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide. And open it up. And here's the trickiest part. See how it's bent like that? Push it open like this, and this is called a pocket fold because you want to make a little pocket and push it up against there. Fold it flat like this, fold this tip down over there like that, then fold it around the back side, then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings, and ta-da, the Sky King paper airplane fold. Now, as Science Maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, Experiments at Large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. Uh-oh, that's never good.
Whoa, Phil, I'm so sorry. You okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents How to Fly Your Paper Airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. High pitch.
Great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah. Yeah? No. Yeah. Yeah is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Here we go.
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace science and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh, yeah, you're
And-
right. The ink doesn't go straight. It follows the wing
follows
down.
the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right, and
generating lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay.
Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out.
I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Okay, be very careful getting off it. Whoa! All right, let's fold it. Nose on that side. Okay.
Remember, we're folding the exact fold we did in the lab, only on a larger scale.
We have a tape malfunction down here.
But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
There.
Perfect.
Yeah. Giant paper airplane! Ha ha ha!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Yep. Maybe.
Like, I'll just.
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah.
Go for it.
Okay, here we go. Wow. What do you think?
Oh man.
I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look. Let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very, very floppy.
Very floppy. What if we supported the plane, like we put struts or something in it, like this stick? If we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like, so
Like
foam
Yeah,
stuff?
and like hollow tubes.
Hollow tubes?
Hollow
Good?
tubes.
Good. So we'll put a whole bunch on there. We'll tape them on so that it doesn't flop around.
Yeah.
We'll try it again.
Yeah.
Yeah, I think we got
Yeah.
something.
Okay, great. Let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
Put that in there, and then that.
Great, look at that. It's not even flopping around, it stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be, well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just...
Phil, there's a lot of stuff on here.
There.
But like it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, let's do it, All right.
Okay.
All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, yeah, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. Hey, Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah,
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up. And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour. All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour. Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly. Oh, woo! There you go, our Mark III model paper airplane. Now, I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap. But we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose.
We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Whoa, okay, all right.
Phil, that was great!
All right!
This throw worked best, but I know what you're thinking. Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is
Largest paper airplane I've ever thrown! Woo! Hey, you guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large. Where were the stairs? Yeah. Oh, never mind, I found them. Science Max!
This episode of Science Max is all about hot and cold. A giant hot air balloon, dry ice, the coldest temperature possible, absolute zero, and whatever this is, Blubber suit! All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. We're gonna be making one of the easiest and one of the hardest experiments to do. Here's what we're gonna make, a hot air balloon. And it's pretty easy to make, that's why it's one of the easiest experiments. All you need is a plastic bag, but not any plastic bag, the kind of plastic bags you get at the grocery store to put your fruit in. That kind of plastic is very thin, very light, good for hot air balloons. And you just want to put 2 paper clips on the bottom of the bag to hold the bottom down. Now here's the other thing you need. You need an adult and a hairdryer. Turn the hairdryer on.
Put the heat on the highest setting and the fan on the lowest setting.
The air inside the bag is getting hotter, which means the molecules are moving faster and they're getting further apart, which means there's going to be less of them in the same space. Less molecules means less weight, and that means it's going to be lighter. The bigger the difference in temperature between the air inside the bag and the air outside the bag, the better it's going to work. So I recommend doing this outside, actually, on a cold day. When it's been long enough, turn the hairdryer off and it will float. Haha! Now it won't float very long because the air inside the bag will quickly return to its original temperature and it will no longer be any lighter than the air outside the bag. But it's definitely fun to fly for a while it lasts. So that's what we're gonna do today on Science Max Experiments at Large. We're gonna max out the hot air balloon and make a giant hot air balloon. Yeah, I know what you're thinking. You're thinking, Phil, they already exist. Why don't you just get a giant hot air balloon? I mean, they're big and you... No. There's no fun in that. I want to make one I built myself. I don't think I'm going to be able to fly in it, but it'll still be pretty cool, I bet. I just need someone to help me. Oh, I know. Michaela from the Ontario Science Centre. Hopefully she's not busy. Hey, Michaela, how are you?
Good, how are you?
Good. I was wondering if I could get your help with an experiment. Do you have some time?
Yeah, I'd love to help out.
Awesome.
Sure.
Okay, let's go back to Science Max headquarters and I'll show you what we're gonna do. Okay,
Nice.
So ready? Here we go.
Oh, no, still here. Still here.
Why are we still here? That's weird. Okay, I know. No? Why is the code not working?
I think it's the Science Center code. Try the
Oh, it's the lab code. Right. Yeah.
Are you okay?
Yeah, no, I'm fine. So, Michaela, I'm glad you're here because today I want to max this out. This is my hot air balloon. It was better before, I smushed it in my pocket, but what I did is I used a hairdryer, and then I put it in and I heated the air, and then it rises up. So in order to max it out, pretty simple. I just get larger bags, right? And then I thought we could cut them and tape them together to make a much larger balloon.
It's a good idea, but you know, if we're making a hot air balloon, we need to make sure our materials are really light. The duct tape seems a little heavy. Even this bag seems a little heavy to me.
In terms of, oh, you mean
terms of
the
weight.
kind of plastic it is might be a little bit.
It seems really thick, this one.
Well, do you know for sure?
I've never tried it before.
All right, well, that's science. We should try it and see what happens.
Let's try it.
Okay, so I'll cut along the side of the bag. You see that? Carbon dioxide gas. Our bodies breathe in oxygen and breathe out carbon dioxide. Did you see it? Oh, take another look. How about now? No, you didn't see it, right? Because carbon dioxide is invisible unless you freeze it. This is dry ice, frozen carbon dioxide. And this is wet ice. It's not really called wet ice. It's frozen water. Now, you know what temperature water freezes at? Starts with a 0, ends with a, well, it's actually 0 degrees Celsius. And this freezes at -79 degrees Celsius. It's much colder. I have to hold onto it with a glove because if I held onto it with my bare hands, I get frostbite. So here's the experiment. If I pour some liquid water on the dry ice, will it freeze again? Let's find out. Because the dry ice is so much colder than the freezing point of the water begins to freeze from the bottom up in room temperature air right before our eyes. Whoa! Totally frozen! Cool! Cool. In order to build our hot air balloon, Michaela and I are taking clear garbage bags, cutting them along the seams so they end up as one thin sheet of plastic, and taping them all together with duct tape into a balloon. Okay, so that's, how many bags is that?
It's like 12 bags.
12, so you think that's big enough?
I think so. It's pretty big.
Okay, I think we can stop there. Okay, so where's the opening again?
I think it's on your side.
I hope you didn't duct tape it close. Okay, no, we're good. We're good. So it's going to inflate like this. Wait a minute. Let's make sure it works. Is it working?
Kind of.
I don't know if it's inflating. Okay, good. So it does inflate. It does hold air.
Yeah.
Right? So should we try it?
Yeah, let's try it.
Okay, so we're gonna use a hairdryer. Right? And now we wait. It's working.
Kind
right?
of.
Oh, yeah.
Woohoo!
Okay, it's almost inflated.
All right.
Okay, what do you think?
Yeah, let's try it.
Okay, on the count of 3, we'll throw it, okay?
Okay.
All right. 1, 2, 3. It didn't quite.
Not quite.
Doesn't quite float,
It's
huh?
still too heavy, Phil. I think we got a couple problems here. The duct tape is really heavy.
Yep.
Also, these bags themselves are really heavy.
Okay, well, if we want to fix the duct tape problem, we could use lighter tape. Like, what if, we use invisible tape, or as I like to call it, science tape.
Science tape.
Which would be lighter than duct tape.
That's a good plan.
But what do we do about the bags?
Have you ever seen those, those dry cleaning bags?
Oh, wait, I've got one. I've got one here.
Cool. Perfect.
Aha!
Yeah, perfect.
Because, when I get my lab coats dry cleaned, so let me see here. Oh yeah, this is much lighter. This is kind of the same material as the grocery store fruit bags, right?
I have a better feeling about this one.
So lighter tape, lighter bag means a much lighter balloon. Okay, well, let's try it. First, I should probably take my lab coat out. This is water. Now, it's ice water. Science! Okay, no, that's not the science part. Here's something you can do at home. Get some ice water and a way to time yourself and stick your hand in the ice water. It's a little hard to stick your hand in ice water for a long period of time because after a while, it starts to hurt. But don't worry, the pain that you're feeling isn't actually because you're damaging anything. It's just your body's way to tell you that you need to take your hand out of the cold water. Yeah, you usually can't do it for very long. But some animals, like seals and whales, they live in ice water all the time. They live in the Arctic, so how do they do it? One word, blubber. Blubber is a layer of fat that protects you from the cold, or protects the seal and a whale. We don't have blubber, but we are today gonna have some blubber because we're gonna make a blubber glove. Blubber glove, I love saying that. Here's how we do it. First, we want blubber. Okay, this isn't blubber, this is lard, which is actually animal fat. You can use lard, you can use margarine or butter or shortening, anything with a lot of fat in it. And remember, this is messy, so definitely get an adult to help you. So we've got our lard, and we need a bag. So what you're gonna do is you're gonna take a scoopful of lard, like this, and you're gonna put it in the bag, like so. Like that. There we go. And then you're gonna start smoothing out the blubber or the lard like this. Because what you wanna do is have a nice thin layer all the way around. See? Starting to work? Yeah. Then seal the bag and tape the edges. A square of blubber. Then do it again. Here I have 2 bags of blubber, and I've taped all the way around the outside. So I have, a blubber glove. Check it out. So let's try it out. I stick the blubber glove in the ice water. It's completely working. It is not even cold. The blubber is completely protecting my hand from the ice water. I'm not even remotely cold at all. That is very fun. So, try it yourself. A blubber glove. Now, how do we max out a blubber glove? Watch. Water, ice water. I know for a fact that I wouldn't last more than 10 seconds in here without my blubber suit. I'm gonna make an entire outfit of blubber. I've got them in large plastic bags, and I'm going to get completely suited up in blubber with the help of Trevor and Stephanie. Okay, guys, suit me up. It's very heavy. Let's just go like this. Oh, okay. Time to cut back on the cookies. All right, let's do it. All right. Blubber suit, go! I can't. Okay. Okay, here we go. Good. Okay, so far. Oh. The legs are warm. And oh, blubber suit! Ha ha ha! I am in seals! Actually, here I am in the ice, and I don't feel too bad. Blubber suit works! Ah, blubber suit's refreshing, actually. You just sit back and chill out. Well, there you go. Blubber suit success. Seals and whales are able to stay in ice water for their whole lives because they have protective layers of blubber just like I do. Okay, so now all I have to do is get out. Blubber suit! Oh no! My blubber is leaking! Ah, I've sprung a leak! My blubber! Oh, my precious blubber! No, what a world! Oh, hey, how you doing? Shut the door, it's cold out there. Cold enough for you, huh? Well, that's nothing. Let me tell you. You know what temperature water freezes at?
Yeah, 0 degrees Celsius, but even that is nothing. Let's say it's winter in Winnipeg. It could get down to -20, maybe even -40, but even that's nothing. Liquid nitrogen, -196 degrees Celsius. But even that's nothing. The vacuum of space, -271 degrees Celsius. But even that's nothing. So, what's the coldest temperature? What's the coldest temperature you can have? It's called absolute zero, -273.15 degrees Celsius. At that temperature, all the little wiggling that particles do comes to a stop. Everything is frozen. No more movement, no more energy. Everything stops. It doesn't get any colder than that. Absolute zero is the ultimate nothing. Brr, time to get your mittens on.
Our first hot air balloon didn't float very well.
It's still too heavy, Phil. I think we got a couple problems here.
So we're making a lighter version out of dry cleaning bags and science tape, both lighter materials than our last version. We also went for more of a square shape than our last version, which kind of looked like a sock. Once we were done assembling, we got the hairdryer and tried it again. Ooh, it's sort of working.
Kinda.
It's inflating. That's something.
It's a start.
It feels warm, like the hairdryer is actually making a lot of warm air in there.
Yeah.
This is definitely working better than the last version because it's so much lighter.
Yeah.
Wait a minute. Almost got it.
Oh,
Yeah, it's sort of working, right?
cool. Kind of.
Okay. Ready?
We testing it?
Turning off the hairdryer. Huh. It kind of collapses the moment we turn off the hairdryer,
Not what we expected, was it?
Yeah.
No.
I mean, it sort of works.
The thing is, our balloon is so big that we need to heat up all of the air that's in there. I don't know if this hairdryer is strong enough.
I think you might be right. So we just need something else that pushes heat.
Yeah, more heat.
So
More
like
power.
a heater of some sort. You know, we've got some heaters up in this room actually, and maybe I could just tear one out. We can use that.
I like it.
Okay.
Let's do it. All right.
There.
Got it.
An industrial heater. And this is going to work just the same as our hairdryer. It's going to blow a lot of hot air up here, but this is way more effective than a hairdryer, right?
Yeah, way more powerful.
So we put the balloon over here, hot air comes up, the balloon inflates, and hopefully flies.
Hopefully.
All right, let's get the balloon. So we put the balloon on the heater and turned it on. But it doesn't seem like much is happening. That's because the heater pushes less air, but the air is much hotter, which means it took longer. Should we have brought a book? But soon it was inflating.
Definitely a better result than the hairdryer.
Okay, you ready? I think it's gonna work.
It's gonna be awesome.
All right.
Yep.
1, 2, 3, let go.
Lift off.
Yeah! It's like a giant jellyfish!
It's huge.
Uh-oh, it's tilting, it's tilting. No, no! Oh no, it's coming back down. Okay, so the balloon flies, which is great.
Awesome.
The problem is it turns over in the air.
Yeah, I noticed that.
And if it turns upside down, then all the hot air comes out and it doesn't fly anymore.
I was thinking next time if we make it bigger, what if we had a little weight at the bottom just to keep it stable?
Oh yeah, okay, I've seen balloons that have sort of an X, like a very light wood that goes across the opening at the bottom.
Oh, cool.
Maybe we could tie a piece of rope to that to keep it weighted. And if the bottom is heavier, then it won't flip over upside down, right?
Love that idea.
So we're gonna weight it at the bottom with a little X so that it doesn't flip over. And we're gonna make a bigger balloon.
We're gonna need more bags.
Oh, right, back to the bag store.
Bag store!
Okay.
Wait for me!
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Strange. This spoon is no sharper than it was before. Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker, and today we're cooking with coal. Today we're going to learn how to make a drink cool. Look at this bottle of lemonade. It's warm right now and not very refreshing. So what's the best way to cool this down? We put it in ice, right? But did you know there's an even better recipe than ice? You can make ice colder. It's true. All you need to do is add salt. I've got a second bowl of ice and a second jug of lemonade, and I've got 2 digital thermometers. What I'm going to do is add salt to this bowl. What the salt does is starts to melt the ice, and that actually consumes heat. This is called an endothermic reaction, and it absorbs heat, which makes the ice colder. And as you can see, this bowl of ice still sitting at around 0 degrees Celsius, but this bowl, -8 and falling. Wow. So there you have it, making something even colder than ice would normally make it. That is a way to make a refreshing glass of lemonade. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
With our new heater and lighter materials, our hot air balloon was floating free. That is, until it tipped over. When that happens, all the hot air inside escapes. But Michaela and I have a solution. So we decided to build an even bigger hot air balloon and add a way to keep it upright.
So the process, aside from that, is pretty much the same. We put the end over top of our industrial heater, and I will plug it in.
Get that hair dryer again for good measure.
It's working, it's inflating, but we gotta keep fluffing it up, otherwise it just sort of sags. But you can see the top of the balloon is definitely working. It's a lot bigger than the last one, though. Do you think we made it too big, Michaela?
It's really big. I think it's working.
It's definitely working. Uh-oh, pull your side.
Oh, man.
Oh, it's totally working! I'm so surprised that this works so well. So the stick is gonna keep it balanced so the bottom faces down, but Michaela's gonna tie a string to the stick so that when it goes up, we can keep it centered. Okay, this looks good. You wanna let it go?
Yeah, are we ready?
Okay.
Okay, 3, 2, 1.
Whoa!
Yeah! So let's recap. The hotter air inside the balloon is less dense than the colder air on the outside. And because we were able to get the air hot enough and the balloon light enough, it floats.
Science Max, experiments at large.
Hot air balloon.
Thank you, Michaela. That was
so cool.
Wait a minute, who has the string?
Oh, no.
Oh no, oh no, oh no!
Science Max! We're flying again on Science Max.
Gliding squirrel.
Throwing things, spinning things, tumbling things, and maxing things out just a little too much.
Go, go, go! Go, go, wait.
Keeping things up in the air is what's on the runway for this episode of Science Max, Experiments at Large.
Well, hello there, Science Maximites. Today, we're going to be flying on Science Max Experiments at Large. Take a look at this. It's my paper airplane. Give her a bit of a throw and she flies amazing. Now, take a look at this. This one is lighter than air. It's a helium balloon, and guess what? It flies on its own. See you later. Well, just hold on a second there, friend. What's this whatchamacallit called? I'll tell you. It's called a hoop glider. Give it a toss and she flies really well. But today we're flying in a whole new way, Science Maximites. I know it sounds like we've covered all the bases for flying, but we haven't. Come on, follow me. Oh, didn't actually realize how much these goggles would fog up. Where was I? Oh, right, we're flying today on Science Max. Come on. Today, we're going to be building a tumble wing. That's a kind of paper airplane that flies on a cushion of air. This is a big mouth tumble wing. It doesn't look like much because, well, it's not. It's just 2 strips of paper taped at either end. But what you do is you throw it in the air and you walk along behind it with a hard surface like this, and that little scoop of air keeps it flying. And here's how you can make a tumble wing of your own. But first, a word about paper. Did you know that paper comes in different weights? The kind of paper you get from the printer is actually pretty heavy. The ideal paper to use for tumble wing making is from a phone book. You may not have a phone book at home. They're kind of rare right now, but its paper is very, very thin and the perfect for tumble wing flying. Now, if you don't have a phone book around, you can use newspaper. It works almost as well. what you do is you cut out some strips of paper, and you just need 2, and you put them on top of each other, and then you offset them, which means you take the top one and you slide it over till there's about maybe a centimeter, 2 centimeters, something like that. And then you take your handy dandy science tape, which is the same as regular tape, except you use this tape only for science. And you tape the edges very carefully like that, and flip it over to the other side. Make a little tape on this side, just like that, and there you go. You have a big mouth tumblewing. Now you also want to tweak it just like you do with a paper airplane. You want to curl the paper a little bit, curl this side a little bit, and let's see how it flies. You'll know you have it right when it doesn't go to the left or right, but just opens up and tumbles straight down. Ah, not too bad. That one curved a little bit, so I'll have to tweak it a little more. Now, the other thing you're gonna need is a nice hard surface. The kind of signs that you get when there's an election are perfect. I happen to have a few of these sitting around, and they are made of something called corrugated plastic. They're very light, but they're also very hard. So you can use this, but you can also use cardboard if you don't have any of these around. So what you wanna do is get your tumblewing and your hard surface and flip it in the air, get it flying very nicely, and then walk behind it with your board, and a scoop of air will be behind it, and it will fly. But it may look easy when I do it, but that's because I've been practicing quite a bit. So here are some tips for tumblewing flying.
Tumblewing flying tips. When flying your tumblewing, you want to be indoors, away from any wind or other kinds of moving air. A long hallway or a big room is best so you don't run out of space. The angle you hold your board is important. Too much tilt or too little and it won't work. Keeping your tumblewing in the air is mostly about the speed that you walk. Too fast and the tumblewing will go over the top. Too slow and it'll fall. Finally, practice, practice, practice. Happy tumblewing flying!
Now I just need an expert to help me. Okay, let's see here. Lisa from Logis Academy. She'd be perfect. Okay. There. And, oh wait, I need a lab coat. Oh, and Lisa needs a lab coat. There we go, Lisa's lab coat. Good, my lab coat. All right, my turn. Oh, my lab coat changed color again. I'll fix it later. Lisa's gonna be here any minute.
Oh,
Hey!
that was so fun!
Oh, did you like the portal?
I loved it, hi Phil!
Lisa from Logis Academy, I'm glad you're here. Your lab coat changed color as well, though. It's supposed to be yellow. I think we had a glitch.
I kind of like it though, blue.
No, but we gotta do yellow. Yellow is the Science Max lab coat color.
Okay.
So, we are here to talk about the tumblewing. I've got my big mouth tumblewing here.
I have
Got
mine
yours?
too, yeah.
Now, what are we want to max it out, obviously. What else can we do?
Well, actually, there's a lot of different designs that we could try. This is a big mouth tumblewing. There's also tumblewings that are just a straight sort of single wing.
Oh.
And then there's some that are like an actual airplane or a glider.
Ooh, and we can max them all out.
Of course.
All right, let's get started.
Let's do it.
And we'll get the yellow lab coats.
And I really like the blue.
We gotta get the yellow. There, now we've got our yellow lab coats. I've got my big mouth tumblewing, and I got my board to push the air.
Oh, look at that! I voted for you.
You did?
I did.
Oh, you were the one. Okay, so let's talk about the science going on behind this air surfer.
Okay, so just like in an ocean, if you were surfing in an ocean, you'd be surfing on a wave of water. Right now, our tumblewing is surfing on a wave of air that you're creating with a board. And air and water are actually both fluids.
Oh, cool. So we
They
can.
behave the same way.
So it really is surfing.
It is surfing. And actually, sometimes we call those air surfers.
Cool. Well, why don't we have a surfing competition? Because I actually have here a Team Phil board and a Team Lisa board. Okay, so what do you want to have a race?
Yeah, absolutely.
Okay, you want to take this one? This one flies really well.
Definitely.
I'll make a new one.
Okay.
Welcome to the Air Surfing World Finals, almost live from Science Max headquarters.
I'm Jim, and I'm joined by Chuck. Today, it's Team Phil versus Team Lisa.
Team Lisa has a lot of heart, Jim.
But Team Phil is on his home turf. Let's see how they do. Round 1 is, of course, the tumble wing race.
And a great day for air surfing. The teams are ready, and there they go!
Ooh, Team Lisa looks like she had some trouble starting. Team Phil has already pulled ahead, but Team Lisa is off the marks now.
I think that beginning fumble might have cost her.
Let's see. Team Phil with a commanding lead, but Team Lisa's catching up. Oh, Team Phil loses his tumbling at the last minute. A great dodge and a pass by Team Lisa. Can she hold it? And no!
Taking 10 steps back is the rule when you drop your tumblewing, Jim. It's anybody's game!
Looks like Team Lisa fumbles her start. Phil pulls ahead. Can he be caught?
Almost at the finish!
Yes. Team Phil with the win! What an upset!
All right, you had a lot of practice with that one.
Yeah, okay, so you got another design?
Yeah, let's try the single wing
New
one.
design.
Okay.
So, at the end of the first round, we have Team Phil with 1 point, Team Lisa with 0.
But now we go to the second round where the design changes. We're now looking at a single wing design. It still tumbles like the big mouth tumblewing, but made from a single wing.
Does that make them harder or easier to fly, Chuck?
A bit harder. They're faster and more maneuverable.
If you wanted to, you could research tumblewing, and you would be able to find this design. And this is what these show you where to fold it.
Yes. So the dotted lines or the dashed lines are where you would fold, and the solid lines is where you would cut.
What's more, Team Lisa has more practice with this version.
And they're off. Oh, Team Phil with another early lead, but Team Lisa's catching up.
Phil doesn't have much practice with this version, and it's starting to show.
You're right, Phil fumbles. Oh, Phil fumbles, and Lisa passes him for the win. There we go. At the break, we're all tied up with Team Phil and Team Lisa with 1 point each.
Look how well mine's going. This is an ornithopter. It's a machine that flies by flapping its wings. When people were still trying to figure out how to get something to fly, they thought, copy a bird. A bird flaps its wings, and it flies, just like this. So, why don't we have airplanes that fly by flapping their wings? It turns out that flapping wings is actually complicated mechanically. First of all, you have to tilt the wing when you go up so it doesn't take as much air, and then turn it so you push more air on the downstroke. So flying like this would be kind of hard for an airplane and really hard to do on a large scale. So humans came up with this, a propeller. Our propeller catches the air, and if you spin it fast enough, it gives you lift. So if you orient it upwards like a helicopter, it will give you lift, or if you orient it this way, it will give you thrust, just like an airplane. So that begs the question, why don't birds and insects use propellers to fly? Turns out, though, that rotating a propeller is really hard to do with something that has muscles and tendons. So in the end, birds fly by flapping their wings, and humans first learn to fly by rotating a propeller. Science.
Lisa and I are air surfing. We've tried 2 different versions of tumble wings, but now Lisa has a new design, one that doesn't spin as it flies.
Okay, so what do you have now?
Oh, check this out, Phil. This is a mosquito glider.
All right, so it's like a paper airplane.
Yeah, but it's not made of paper. It's made of a light foam.
Ooh. The mosquito gliders work the same way as the tumble wings, but because they're much larger, they're much harder to control.
I got it. Oh, no, 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 no. Oh, almost into the stuff. Not bad, though, right?
You got it.
This is very tiring.
This is really hard. It takes a lot of flying time to master.
We got the hang of it, but we quickly learned that you have to run a lot faster with the gliders. And we were soon out of breath.
Whoa, sorry. You gotta be in good shape for this.
Turns out a bigger glider is much harder to fly. So,
Ultra maxed out mosquito glider.
we made it even bigger. Why? Well, because it's Science Max.
Bigger board.
We needed a much larger board and tried first with 2 people.
Ready? Going.
And then with 1. And the most we were able to get it to fly was... not a lot. Our conclusion?
Large airplanes just don't fly very well.
Well, homemade ones.
But we can try something else.
Okay.
Let's try something else.
Let's try something else.
I got a super special on anything that can fly. Go on, pick something out. Oh, you had the paper airplane. Oh, good choice. Good choice. But guess what? Paper airplanes don't fly. Full price. Yeah, I know, but before you start arguing with me, you need to know the difference between flying and gliding. A paper airplane does not fly, it glides. You need constant thrust in order to fly. If you do not have constant thrust, then you glide. Take this bird. This bird can fly because it flaps its wings. It has constant thrust. On sale. But this airplane cannot fly. You give it some initial thrust when you throw it, but after that, it can only glide. Full price. But look at this. It's an airplane powered by a propeller on an elastic. Now we're talking constant thrust. It can fly! On sale! But it can get confusing. I mean, look at this flying fish. Nope. Flying fish cannot fly. They can only glide. Full price. Look at this. It's a cute little flying squirrel. He climbs a tree, jumps off from a high branch, opens his legs, and there's a little flap of skin there that allows him to sail to another tree. Haha, flying squirrel. No, not flying, no constant thrust. Gliding squirrel. Full price. Okay, tell you what, you came all the way down here, I'll make you a deal. Check this out. Flying fish, now it has a propeller, it has constant thrust. It flies for real. And ditto, squirrel with a jet engine. And now you know the difference. Something that flies has to have constant thrust. Otherwise, you're just gliding. Squirrel away! I forgot to gas him up.
Look at those clouds. Aren't they nice? Did you know there are different names for clouds? Like those clouds right there? Those are cumulus clouds. They're the kinds that look like cotton balls, really fluffy and light. Well, they're not exactly fluffy and light. First of all, they're not fluffy, they're wet. It would be sort of like being a very dense fog, and it'd be very wet if you were in that cloud. And they're also not light. In fact, they're not light at all. That cloud right there weighs about 500,000 kilograms. That's the same as 100 elephants. 100 elephants just floating around in the sky? Come on, how does it do that? It does that because it's so spread out. But water is very heavy. Interesting to think about. 100 elephants just floating around in the sky above our heads at all times. Almost makes you want to go inside.
Our air surfing tumblewings worked well, but our mosquito gliders were a bit too maxed out to fly really well.
Large airplanes just don't fly very well.
Well, homemade ones.
But maybe we should try maxing out the tumblewing just to see what happens. So we did.
Okay, Lisa, I'm gonna throw it, and then you're gonna push the sign.
What?
Go! Wait.
Oh, did it go? What happened?
It didn't, whoa, it didn't work.
We tried it and tried it. And it turns out, yeah, it doesn't fly.
Go, 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 go! Go, go, wait.
But I mean, this is science, Max, so of course we had to at least try maxing it out.
Phil.
I don't know if this is working.
It's heavy.
It's very heavy. Okay, maybe we should go back to a slightly smaller version.
Sounds like a plan.
Okay.
High five?
High five. This is a boomerang. Boomerangs are from Australia, and the cool thing about boomerangs is when you throw them, they come back. With practice. That was close. When you throw them, they come back. And it comes back. Comes back. Come back. Come back. So, why does it come back?
Well, if you take a look, it's made of two wings, like airplane wings, but with one important difference. You see, a wing has a shape called an airfoil, and this gives lift.
But check it out. The boomerang has one airfoil pointed this way and the other pointed the other way, which means if you spin it in the right direction, each wing will get lift as it rotates. But how does lift make it come back? Well, that's the trick. You see, you throw it sideways. The lift from the wings makes it go in a big circle and come back to you.
So when you throw a boomerang, this side starts to go this way and it gets a little bit of lift. Then this side gets a little bit more lift, and then this side gets lift, and each time it gets lift, it starts to turn just slightly. So as the boomerang spins, it describes a nice big arc in the sky and comes right back to you. Ha-ha! And that's how a boomerang works. Thanks, Phil. No problem, Phil. Hey, do you want to get lunch? Yeah, lunch sounds good. Okay, come on. Well, the Science Mech headquarters has a nice cafeteria.
We've tried air surfers of all shapes and sizes. And what have we learned?
Maxing out an air surfer by making it bigger is really difficult.
Very difficult, yeah.
So what we've decided to do is go back to our original big mouth tumble wing and instead do it on a maxed out obstacle course!
Tumbling surfing round 3, the maxed out obstacle course. Let's take a look at the obstacles. The tree slalom, the podium ramp, the hanging hoop, ring walk, wall of boxes, ladder tunnel, side hoop, ball promenade, and the barrel run.
So here's how we play. I go through and then you follow me. And if you make it through an obstacle and your tumblewing's still in the air, you get a point. And at the end, we count how many points we have and we see who won.
And it looks like they're ready to start. Here we go!
Where are you, Team Lisa? Oh. Oh, yeah. Oh, no. Okay, what do I do with the boxes? What do I do with the boxes? Going through the boxes! Definitely didn't make that one. Recover! Ah! Oh. Okay, definitely lost a point there.
I'm almost there! Right behind you!
Knock the barrels over, getting
I
through
get
the
an
finish
extra
line.
point for
And Team Lisa. Oh, yeah! Nicely done, high five.
Awesome.
See how the airflow from the board keeps the air surfer in the air? Well, the trick is to give it just the right amount of air to keep it in control. Not too fast and not too slow. That's the science to good tumblewing flying. So, with the points from the last round added up, Team Phil and Team Lisa are tied again.
You know what that means? Tiebreaker! Thanks very much for watching Science Max Experiments at Large Tumblewings. You want to go first?
I do, let's do it.
Okay, you go first this time, and then I'll follow you. I think it's easier to go first. So, okay, ready?
Yeah.
Ready, set, go.